ME 204, Equation of Motion for General Plane Motion of Rigid Bodies. So far, we've looked at what happens when a body translates. For example, if we've got this rod and it moves in a circular path, like this, the object is translating along that circular path, and we can denote the accelerations with a tangential acceleration and a normal acceleration. We've also looked at what happens when we have a body that just rotates, that's pure rotation. In this case, we have the rod that simply rotates, and we represent this with the mass moment of inertia about the center of gravity times the angular acceleration. So what happens when we have both rotation and translation? For example, maybe we have a rod that's pinned at one end. If we look at just the translation of that rod, it moves along the circular path. But we also have rotation that occurs to get the rod to the point where we would expect it to be. And we represent the rotation with the mass moment of inertia times the angular acceleration. If we put all of it together, then we can represent that general plane motion by drawing at the center of mass our tangential acceleration, our normal acceleration, and the rotation. What are kinetic moments? Well, we're familiar with moments of the force. We did this in statics. Moments of mass, which is a mass times a distance. Moments of area, an area times a distance, which we use to find the centroid of an object. So why not kinetic moments? These are moments computed from the kinetic diagram that we draw when we solve our problems. Basically, our kinetic moments are moments of our mass times acceleration, or a mass times acceleration times a perpendicular distance to some point of interest. We call these kinetic moments, which is equal to the mass times the acceleration times the perpendicular distance at the center of gravity, plus the mass moment of inertia at the center of gravity times the angular acceleration. Here's an example. How fast does a bicycle rider have to accelerate to just barely bring the front wheel off the ground? Well, we start these problems by drawing our free body diagram. So let's look at the free body diagram for the bicycle with the rider. Well, the rider has a weight, the bicycle has a weight, there's a normal force that occurs at the back wheel, and a friction or driving force at the back wheel. And we may also have a normal force at the front wheel, but in this case, we're looking at the point when the front wheel just comes off the ground, which means that normal force at A will go to 0. Next, we need to look at the kinetic diagram. What's happening with this bicycle at this point in time? We know that the bicycle has to be accelerating in order for that rotation to occur. So we have a mass times acceleration of the rider, a mass times acceleration of the bicycle, and we may also have a rotation of both the rider and the bicycle. But in this case, we're saying that we just want to barely bring the front wheel off the ground. So our rotation has not yet really started. So we can say that our mass moment of inertia times our angular acceleration is 0 for both the rider and the bicycle. With our free body and kinetic diagrams drawn, we can now come up with the equations that we need to solve the problem. We can look at the sum of the forces in the x direction, the sum of the forces in the y direction, and summing moments to solve this problem. Let's look at the sum of the forces in the x direction. This would be equal to the mass times the acceleration in the x direction, or the sum of the forces in the x direction cause the masses to accelerate in the x direction. In this case, we have the driving force of the bicycle is equal to the mass of the rider times the rider's acceleration, plus the mass of the bicycle times the bicycle's acceleration. We're assuming that the acceleration of the rider and the bicycle are the same, that they move as one. We can also look at the sum of the forces in the y direction, which is equal to the sum of the masses times the acceleration in the y direction. In this case, our acceleration in the y direction is 0, so we simply have a statics problem. The normal force at point B at the back wheel of the bicycle minus the weight of the rider minus the weight of the bicycle equals 0. What about looking at moments and kinetic moments? If we sum moments about the point B on our free body diagram, we also have to sum kinetic moments about the same point on our kinetic diagram. If we do this, it eliminates our normal force at B and the driving force at B, making this problem much easier to solve. So let's write our equation. We would have the weight of the rider times its perpendicular distance to the point of rotation, plus the weight of the bicycle times its perpendicular distance to the point of interest, is equal to the mass of the rider times his acceleration, our mass times acceleration at this point, times the perpendicular distance to the point of interest, point B, which is h1, plus the mass of the bicycle times its acceleration, times its perpendicular distance to the point of interest, point B, which is h2. Filling in what we know for our weights and our masses and our heights. If the weight of the rider is 165 pounds and the weight of the bicycle is 30 pounds, the distance d1 is 1.5 feet, the distance d2 is 2 feet, h1 equals 2.5 feet, and h2 equals 4 feet. Plugging those values into our moment equation gives us this. Then all we have is one unknown, the acceleration of the bicycle and the rider. Solving for the acceleration, we get that the acceleration is 13.5 feet per second squared. I could have taken a moment about any point on that bicycle and used that same point on my kinetic diagram to take kinetic moments. I chose point B as stated earlier so that we could eliminate some of the forces making the problem solvable. So let's summarize the equations that we can use. First of all, we have the sum of the moments about the center of gravity is equal to the mass moment of inertia about the center of gravity times the angular acceleration. This is valid in all situations where we have a single center of mass. We can also use the sum of the moments about an offset point is equal to a shifted mass moment of inertia to that point using the parallel axis theorem times the angular acceleration. We use this when an object is rotating about a fixed axis. Finally, we can use the sum of the moments about an offset point is equal to the sum of the kinetic moments about an offset point. This is valid in all situations. We can always use this equation. We've looked at a problem where we dealt with shifted rotation, where we shifted our mass moment of inertia to solve for the angular acceleration of a rod that's pinned on one end. But what if we wanted to know what the reactions were at point O? Well, we have our free body and kinetic diagrams, but we may not be able to solve this problem for the reactions with what we have on the kinetic diagram shown. We need to draw our kinetic diagram with everything shown at the center of mass. In this case, we have tangential acceleration at the center of mass, normal acceleration at the center of mass, and rotation of the center of mass. So we can solve this problem using the second kinetic diagram and kinetic moments. We know that the mass moment of inertia about the rod is 0.667 kilograms meters squared. Using the conventional notation for positive and negative, we can sum the forces in the y direction, which is equal to the mass times the acceleration in the y direction. In this case, the reaction at y would be equal to the negative mass times the tangential acceleration, since it's pointing downward. So our reaction at y is equal to minus 2 times the tangential acceleration. We can also sum the moments about an offset point, which is equal to our kinetic moments. In this case, the weight of the rod times the distance to the point of rotation, point O, is equal to the mass moment of inertia times the angular acceleration of the rod, plus the mass of the rod times the tangential acceleration of the rod, times its perpendicular distance to the point of rotation. Filling in what we know, we would get this equation, but we still have an alpha, an angular acceleration, and an a sub t, our tangential acceleration. If the sum of the forces in the y direction is our first equation, and this is our second equation, we have two equations and three unknowns, so we need another equation. In this case, since we have a fixed point of rotation, we can state that the tangential acceleration is equal to the angular acceleration times the radius from the point of rotation. Our radius in this case is 1 meter. Now we have a third equation. Using these three equations with the three unknowns, we can solve them simultaneously to find that the tangential acceleration is 7.36 meters per second squared, our angular acceleration is 7.36 radians per second squared, and our reaction at y is equal to 14.7 newtons. Notice that we had nothing in the x direction. We assume that this started from rest, which means that our initial velocity is 0, meaning that our normal acceleration would also be 0. Summing forces in the x direction means that the reaction at O in the x direction would be 0. Our next topic is the equation of motion for rigid bodies, slipping versus tipping.